Hey, this is a video for 6.6, nuclear power. So go ahead and check out the overview and set up your guided notes. So we have two types of nuclear reactions. We have nuclear fission and nuclear fusion. Nuclear fusion occurs on the sun, and it is when you are making a larger nucleus from smaller nuclei. Like, for example, on the sun, hydrogen atoms are combined into helium. So this is under huge amounts of energy, releases huge amounts of energy. This is something that scientists have been trying to replicate on Earth. We just haven't been able to. But if we were able to replicate it, it would be a game changer in terms of energy, because there's a lot of energy released. Now, the process of nuclear fission is when you're taking a larger unstable nucleus, in this case, uranium-235, and recall that 235 refers to the amounts of neutrons and protons that are in the nucleus, and you are breaking it into smaller substances. Now, the only problem is we don't really have a lot of uranium-235. We got a lot of uranium-238. So the uranium that we are mining contains predominantly uranium-238, and we need to enrich this in a manufacturing facility. So first it needs to be enriched into uranium-235, and then you can complete the process. But when this is done, what you do is, this is under controlled settings, but you would bombard it with a neutron, and this causes a chain reaction. So when a neutron hits the uranium-235, it breaks into two smaller atoms, and you don't have to know what they are. In fact, I think one's krypton, one's barium. It doesn't really matter because you don't have to know. But what also happens is there is a huge amount of energy released. Huge amount. And also two extra neutrons are released, which these two neutrons can then each go and bombard another uranium atom or nucleus, which then can cause a huge chain reaction. This has huge amounts of energy that are released. In fact, there is so much energy that we don't want to have this all happen at once because it would be a huge explosion. So what it is they have these fuel rods which contain the uranium-235, but there's also these control rods which will absorb some of the extra neutrons without actually changing themselves. So the fuel rods and the control rods are working together. The control rods go down and slow down this reaction so it doesn't all happen at once. Now, this is very similar to the other system to generate electricity. The only difference is you have the control rods and the fuel rods, and this is within a containment structure, which is usually like very, very thick concrete or other thick material, and this is to prevent any sort of escape of radioactive particles if there is some sort of explosion or meltdown. But what happens is when you are using the fuel rods, you will have that reaction occurring, the reaction that I told you about. And then what happens is that will release so much energy that it converts the water into steam. And the process of turning the turbine, spinning the generator, generating the electricity is the same. Now again, the fuel rods contain the uranium, and you are bombarding the fuel rods with the neutrons, and that is creating the chain reaction. To slow this down, they have the control rods that get in the way of this chain reaction. So the control rods are doing exactly what the name says. It's controlling it. Now, the hot water is also going to the cooling tower, and this cooling tower is where you have large surface area to allow the heat to dissipate. If you've ever seen the beginning of The Simpsons, Homer Simpson works at a nuclear power plant. The cooling tower has this big giant, it's big giant, it has a lot of surface area, and a lot of times you may see what looks like smoke coming from the top, but it's really water vapor. Eventually, when the water is cooled enough, it can go back to a reservoir and then be recycled back into this process. So there are some calculations that you will need to perform. I am not going to go into a whole lot of detail because I have a separate video specifically for half-life calculations. But half-life is something that you would have done in chemistry. And there is a system, so I'm going to encourage you to look at the video for half-life calculations. It's a Master the Math hack. And basically, this would be like, if this is uranium-235, then whatever the half-life is, it's several years. But after one half-life, you're going to have half remaining, and then a quarter, and then 12.5%, 6.25, 3.125, 1 point, it's going to get smaller and smaller and smaller. So you have to calculate either the total time elapsed, you have to calculate how much remains, or you have to calculate how long a half-life is. And this is something that you'll be practicing plenty of times in class. Now, the nuclear waste, when it is spent, it is still radioactive. And any of this spent nuclear waste, when something is radioactive, it is releasing radiation, and that can cause genetic anomalies. It can cause mutations, which is, a mistake or a change in the DNA. So we have to figure out a place to store this spent waste so it's not releasing radiation, sometimes for, millions of years. So this needs to be done at some place. Now, there was a proposal to do it in a place in Nevada called Yucca Mountain, which is in the middle of the desert. And the reason for this is that if there was some sort of disaster or explosion, that's very low population density, so it would, not really affect a lot of people if it were to have some sort of destructive explosion. It was very controversial because people were like, why do you have to put it in our area? And also, Nevada didn't have any nuclear power plants. So they're storing waste in our backyard. That's a major issue. In fact, this acronym NIMBY, N-I-M-B-Y, stands for Not in My Backyard. So this is one of these NIMBY concerns. And this, again, is why it was so controversial. Eventually, it was defunded in 2010 during the Obama administration because there was so much controversy. Oops. So instead of storing it at a central location with all the nuclear waste, the nuclear waste is now stored on site. And it's stored in an area that is underwater. And this water is kept cool, and it is kept at a specific temperature. Water, remember, has a very high specific heat, so it can absorb a lot of energy without actually increasing the temperature. So again, it's stored on site, underwater. This is a very expensive process. Now, there are some environmental impacts of nuclear power generation. For one, you have to deal with this radioactive spent fuel. You also have the mine tailing. So anytime you're mining for the uranium, you have the impacts from mining, but you also have the impacts from the uranium purification. So when you're enriching the uranium, it requires a lot of fossil fuels for that and requires other resources as well. Also, you're using a ton of water, a lot of water for the generation of the electricity. You need the water to convert to steam, which is turning the turbine. And that can lead to thermal pollution if it does get out into a body of water. Thermal pollution is just another way of saying like hot water. Now, this facility is actually the Indian Point Power Plant. It was recently decommissioned. It's in Westchester. It's the closest nuclear power plant that we have to New York City. It is no longer in operation, but it is in Westchester County. Now, there's been 3 major nuclear disasters in our history. The first one was in 3 Mile Island, and that is out in Pennsylvania. What happened was a cooling valve was closed, which caused a partial meltdown. And a meltdown is just a way of it's a potential some level of malfunction. So a complete meltdown would be like an explosion where radioactive particles are released into the environment. 200,000 people were evacuated from the vicinity, and there may have been higher rates of infant mortality and potential cancer rates from the radiation that escaped to the neighboring towns. Now, the most famous and the biggest disaster was in Chernobyl, and that was in Ukraine. At the time, it was the Soviet Union, but since they've broken up, now it is Ukraine. The control rods were actually removed, and that causes an overheating, which then led to a fire and an overall explosion. This is the containment structure. They basically had to put cement on top of it to kind of contain everything after it exploded. There was huge contamination, widespread contamination, and there were 31 people died in the actual explosion, and up to 3.5 million people were affected by the radioactive gas, or the radioactive particles. There's a lot of resources. There was actually a mini-series on HBO called Chernobyl that talks about it. There's been a lot of studies about the impacts on plants and animals after exposure to radiation. So you're free to, do a Google search on that information. And the most recent one was in Fukushima. Oh, by the way, Chernobyl happened in 1986 and Fukushima happened in 2010. Fukushima happened in Japan. It started with an earthquake, which then led to a tsunami. And a tsunami is just a giant tidal wave, which then flooded the plant. That caused structural damage to the facility, which then led to fires. And the fires led to a lot of hydrogen explosions. And the hydrogen explosions, this is one of the things you see right here, destroyed 4 out of the 6 reactors. And they had to evacuate 100,000 people. And Fukushima, the radiation spread for many miles, and the air currents, potentially could blow some of that radiation to the United States over the Pacific Ocean. What I would like you to do is respond to this check for understanding. And finally, for our FRQ practice, I want you to describe a drawback to nuclear power generation. I hope that this video was informative. I thank you for your attention, and I will see you soon.